Hi and welcome to Unit 3, Topic 2, Video 1. And in this next following series of videos we're going to be looking at a vector review in preparation for the big vector topic in Unit 3. So this should just cover off on everything you've done before, introduce a couple of new things and really get you ready. Make sure you're asking questions though and you're all over this work. So there's our learning goal success criteria as usual. It's quite a big OneNote this one, so that encapsulates a lot of things. Now let's have a look at stuff that you should or need to know. Starting with notation. So vectors can be written in a few different ways, and you'll know them as these column matrices. So they're a really common form of vectors, and you can technically write them as a row matrix, but that's really uncommon. Or you might recall writing them down as 3i plus 2j. So vectors, when they're split up into their components, I and j being the unit vectors in different directions. And they're usually drawn visually as line segments in 2 dimensions for 2D vectors or 3 dimensions for 3-dimensional vectors. So that will be the line segment that is 3, 2, representing that vector 3, 2. So there's our option. Now of course this line segment is the same vector anywhere on the page, but often we'll be starting it at 0, 0, or the origin, and hanging out to here in most of our diagrams that we draw. But I can transport that vector anywhere on the 2D plane, on the Cartesian plane, and it's an equivalent vector. It doesn't actually change it. The magnitude of vectors you'll need to be aware of, and the magnitude of vectors such as that vector, 3, 2. The magnitude, if we call this vector x, the magnitude of x is written like this, and it's equal to that Pythagorean relationship, 3 squared plus 2 squared, which in this case is the square root of 13. Not all that nice, but that's what it's equal to. Arithmetic of vectors, hopefully you remember adding, subtracting and scalar multiplication and some of the visual representations of this. So let's say that we have vectors x and that's equal to 3, 2, the one we've just been doing, and vector y, and that's equal to negative 4, 7. Well then we get this, x plus y is equal to 3, 2, plus negative 4, 7, and that of course is equal to negative 1, 9. And we also get our subtraction happens the same way, and scalar multiplication, 3x minus 2y, well we'll just do that scalar multiple there, which is 3 times 3, 2, minus 2 times negative 4, 7. This will be equal to 9, 6, minus negative 8, 14, and 9 minus negative 8, 6 minus 14. I'm really doing this longhand, so you don't have to go quite this far, but I end up with 17, negative 8 as my vector there. And our visual representations as well. So say for example, we have vector x. Vector x is, I'm going to have to give myself space here. I might even just shoot across. So vector x is here, and it's 3, 2, and y is negative 4, 7, which is going to take it somewhere up to about here. My scale's not perfect obviously, but it's okay. And x plus y will be x, and then we go y, this is a top to tail method. So we go y from the end of x there, and this is our vector x plus y. X plus y. That's our geometric representations of that x plus. And our x minus y will be in this direction. So our geometric representation of x minus y is there. Noticing that this is also the same as the other diagonal of the parallelogram that x and y make. Now it's not necessarily a rectangle, it looks a bit like a tilted rectangle in this case, because this kind of looks right angled, but we don't know whether that's right angled. It is a parallelogram though, because the other side here, this is x, and this is y, and that's the geometric interpretation. And there's lots more to it, but that's the general principle that you'll see. And you'll also need to be aware of the 0 vector, which is just 0, 0 in 2 dimensions, or 0, 0, 0 when we get to the 3-dimensional vectors, so you know that. And a unit vector, so the unit vector is a vector such that the magnitude equals 1, and the unit vector for x is written as x hat, and it has a magnitude of 1, and x hat is equal to x divided by the magnitude of x. So in this case it would be equal to x, which was, so to be the magnitude of x is 1 on root 13, we've done that calculation before, and then 3i plus 2j, that's our x vector. Now parallel vectors, we know that two vectors, u and v, u is parallel to v if and only if u equals kv. So we're saying that u is some scalar number bigger than k. That makes them parallel. So u could be this vector, k would have to be some other vector longer, the magnitude doesn't matter, but the direction has to be the same. And for the direction to be the same, the proportion, or the rise over run, would have to be equivalent. And that's why we don't get a change in our I component and then no change in z, or vice versa, because that would then change the direction. So we get this result. And of course the polar form of a vector, so the polar form of a vector is x, which is currently 3i plus 2j. Well, we do a polar form by saying, instead of representing it as 3i and 2j, i.e. this triangle with, that should be a 3 and 2, let's represent it instead as the directional angle, as in the angle measured from the positive x-axis, and the magnitude of the vector. So polar form is going to be equal to r, which is equal to the square root of 13, we've done that calculation before, and theta, which is tan inverse of b over a. We have to be quadrant aware here, so it's tan inverse of 2 over 3, and now we're testing me, but I've got a calculator here, so we'll quickly pop that in. Shift tan of 2 over 3, we close that bracket, and we come out with 33.7 degrees. I should really flick across the radians, but 6.9 is closer. So we'll go in degrees, and this gives us x is equal to root 13, 33.69. And that tells us the direction and distance of x, which is another way of defining a vector called polar form. We're going to do a bit more work on that in 3 dimensions in this topic as well. And then lastly, we talk about the scalar product of two vectors. So the scalar product is that dot product, x dot y is equal to x1 y1 plus x2 y2, and it's also equal to the magnitude of x times the magnitude of y times cos theta, which is the angle between. Now we can calculate this for our x and y before, so this is 32.47 is equal to 3 times negative 4, that's pretty bad, plus 2 times 7, which hopefully you see, well that's pretty bad notation, that's equal to 2. Now we also know that the magnitude of x is equal to root 13, and the magnitude of y, I'll just do this quickly, it's equal to the square root of 16 plus 49, which is 65. We could actually use that information here to work out a value of cos theta, because we get the dot product is equal to 2, and that's equal to the square root of 13, interestingly, times 65 cos theta. 65, and I've written 16. And that actually comes out to be 13 root 5, but that doesn't really matter. We could rearrange that to find theta. We can use that scalar product to find an angle between, and a few other things as well. Worth going back and having a look at that if you need to. Well, there's the end of video 1, where we've summarised a whole bunch of stuff that you need to remember about vectors. I hope that's gone well, and if there's anything there you need to review, definitely make sure that you go back and have a look at it. All the best.